Welcome back to Finite Element Methods. This is class number 22. We're talking about, well, we just finished our discussion about um, finite element methods for parabolic problems, for diffusion problems in particular. And now we're going to change topics a little bit and start talking about um, Stokes problem, which is It's Stokes problem is highly related to a parabolic problem because it's related to the Navier-Stokes problem by assuming the time derivative is equal to zero essentially. And we'll get on to that momentarily. But there were a couple of things that I wanted to clear up um, related to the discussion we were having last time. And it had to do with these Bochner spaces. These are the spaces that have the form LP0T LQ. Or if in the case where the functions are differentiable, weakly differentiable in time, then we might write something like this, H1 0T L2. So what do these spaces mean? Well, there's a lot there to unpack, but let me give you a kind of superficial definition or a superficial meaning. So if I say that F is in this space, LP 0T LQ, this means that the following integral is finite. Integral from 0 to t, the norm of f of t, and it's the LQ norm that's associated with this guy, raised to the p power, so the p is coming from here. This norm, this integral is less than infinity. It's finite. Now, actually, this is not a norm. The way we get it to be a norm is to take the pth root of this thing. So if we take the pth root of this, then this becomes a norm. We're not interested in that. We're just interested in knowing that this integral is finite. Now, if I say that f is an h1 0tl2 function, what does that mean? It's similar to what we have above, except that it means both the function and its first weak partial derivative are in this space L2 0tl2. And this harkens back to what we knew about h1 functions to begin with. If we were talking about spatial h1 functions, then these are functions that are themselves L2 and the weak derivatives up to and including all the first order partials are all in L2. Well, here we're thinking about functions of time, so the only derivatives are the zeroth order derivative is the function itself, and the first order derivative is well, it's the only partial derivative, it's just the time derivative. All right, so what does this mean? For example, this guy here. This means what we wrote above. This simply means that the time derivative of the function f, if I take the L2 norm and square that, and then integrate from 0 to t, this guy is finite. Okay? So that's what these Bochner spaces mean. Now, last time I told you remember I was puzzled. Why wasn't I using a 2 here? Well, the 2 didn't come up in the analysis, so we didn't need it. But it suffices to assume that f is in this space to know that this integral is finite. Let me show you how this is possible. Suppose that f is L2, 0t L2. So normally, remember what I said above, if I have a p here, then I'm going to take the p power on the norm. But you only see a 1 power there, so there seems like there's something off. Well, in particular, if we know that this is in L2, L2, then we know that this integral is finite with the 2 there, with the square. But we also know that the integral with a 1 here, power 1 on this norm, is also finite. And let me show you why this is true. It's just a simple application of the Cauchy-Schwarz inequality. So we want to show that this object here is finite. How do we do that? Well, let's rewrite this as this integral, or this integrand. Let's rewrite it as the thing that we have in the integral on the left times 1. And now we're going to apply Cauchy-Schwarz inequality with this function and this function as being two functions we're assuming are functions of time. And we're not assuming, we're viewing this as an inner product over the time interval 0 to t. So this is just an inner product, a standard L2 inner product actually, over the time interval 0 to t. So I can apply Cauchy-Schwarz to this. Now, normally we've been applying Cauchy-Schwarz in the spatial setting, but it can also apply in the temporal setting as well. So if I apply Cauchy-Schwarz, I'm going to take the norm of this first guy, right? And it's just going to be the standard L2 norm in time, and the norm of this guy. So what I get when I get the norm of this guy, well, this is just a finite number. This is just going to be what? The square root of t, because this integral is going to be t, and I take the square root, I get square root of t. What about this? This is also finite by our assumption here. So we know that if this integral is finite, then this integral has to be finite just by the Cauchy-Schwarz inequality. So that's why it sufficed in the work that we did in the last two classes to assume something like this, even though we weren't putting the square on this integral or on this integrand, we were only using the power 1. This integral turns out to be finite. We don't have to assume anything else about it. So that's just one little thing I wanted to address before we get started with the Stokes equation. Stokes equation. This is a fluid flow equation, and it's highly related to the Navier-Stokes equation. We're not going to derive this. I'm not going to derive it from Navier-Stokes, but I will say a little bit about it. Well, let's at least address what we mean by these variables. So U in the Stokes equation is the fluid velocity. U is a fluid velocity. So what do we mean there? So at each point in space, so we've got some sort of domain, and at each point in space, I need to assign that a value of a vector. And I'm gonna assume that, or I'm gonna visualize this in the following way. I've got this point x in space, and this value of this vector at that point is what I'm going to call or assign to be u, my fluid velocity. So at each point in space, I have another vector, right? And so maybe this fluid flows around the container like this. Okay, so kind of swirls around this container, and our container is our domain omega. Okay, so these guys are the velocity u at different points. So we call this a velocity field. What about this variable p? P is what's called the pressure. So that's a scalar. And F is a forcing term. So this might be something like the buoyancy force. So for example, if I have a fluid and it has different densities, then this could be the gravitational force. And we'll actually get into this in depth in my next class, which is non-equilibrium thermodynamics, but I'm just going to leave it at that. This is some sort of body force. It could be the buoyancy force, for example. All right. Now, so this equation is some application or some approximation of the conservation of momentum equation. So this is an approximation of the Navier-Stokes equation, or at least the momentum conservation part of the Navier-Stokes equation. The second equation is what we call the divergence-free condition. This is also where this derived from the conservation of mass. Okay, so notice that everything makes sense here in terms of units. If I take the divergence of a velocity field, I should get a scalar. So that's equal to this scalar, 0. Okay, that's the divergence-free condition, or also called the mass conservation equation. Let's look at this equation. Well, we've got to figure out what this Laplacian means when I apply it to this vector function u. And here's what I mean by that. So the Laplacian is typically a scalar function. You can think about the Poisson equation that we've talked about previously. I apply the Laplacian to a scalar function u, and I could set that equal to a scalar forcing function f. Well, in this case, we're going to apply the Laplacian function to each component of u. So u is a vector function. It's got different components. So what we mean by this is if I apply the Laplacian to this vector u, what it means is it's Laplacian of the first component minus Laplacian of the second component, and so on. You just apply that Laplacian operator, or in this case, negative Laplacian operator, component-wise. So that returns a vector when I apply this Laplacian to this vector. So does this term make sense? Well, we said P is a scalar. When I take the nabla operator, the gradient operator, acting on a scalar, I get a vector. So this is a vector plus a vector equals a vector. So f is a known function, and we're looking for u and p to satisfy this equation. Of course, now I'm looking for two variables. Actually, if I'm in 3D, this is three equations. In general dimensions, there are d equations. And how many variables are really in u? Well, u has d components, so these are d components to determine u. But I actually need one other equation because I have another variable in the system, namely p, the scalar. So I need one equation to solve for that guy to close the system. To fully close the system, I also need what are called boundary conditions. I missed the arrow here. So the boundary conditions are, in this case, of the type we call no slip. So u is not allowed to be anything other than 0 on the boundary of this domain. Okay, so again, if you take my class on non-equilibrium thermodynamics next semester, we're going to explain where all this comes from. This is called Stokes equation or Stokes model. Now we're going to play the same game that we've always done with this, and we're going to derive different types of solutions. If we want to use the finite element method, then we've got to derive what's called a weak formulation of this problem, or in other words, a weak solution. But before we even get onto that, let's define what we mean by a classical solution. So we say that u and p, that pair, is called a classical solution to the Stokes problem if and only if u is, well, it's a vector function. So when I apply this notation here with the superscript d, this means I'm going to apply to each component this requirement, whatever is in this bracket. So for the first component, I'm going to require that it's a C2 function over omega and a C0 function over omega closure. So each component, I'm requiring the same thing of that. For each component, I'm requiring the same regularity. So we use this notation to designate that. Now for P is not required, P is a scalar, so I only have to give, I don't need brackets around this. I only need to designate what I want the regularity to be for that scalar. Well, for this equation to make sense, I've said that I had to have two derivatives of u. That's because I'm applying the Laplacian operator to u. The boundary conditions here are why I'm considering this to be a C0 function on omega bar, because that's the only way that I can make sense of these point boundary conditions. For P to make sense, in a classical setting, then I'm going to require P to be a C1 function over the domain, so that when I take this, I get when I apply the nabla or the gradient operator to P, I get a scalar continuous function, or sorry, a vector continuous function. So all I have to assume about f is maybe that it's continuous, this is going to be continuous, and this is going to be continuous, and everything will make sense in sight. So if u has this regularity and satisfies this equation, or this problem pointwise, then we say that up is a classical solution to the Stokes problem. Now, what we're going to play the usual game to get a weak solution, we'll multiply by a test function and integrate by parts. The first equation, or to the first equation, I'm going to multiply a vector test function called v, and then I'm going to integrate by parts. I can still do all that. And I can even integrate by parts on this term. If I multiply by v and integrate over the domain, well, you'll see what you get in a moment. UP is called a weak solution to the Stokes problem if and only if U has this regularity. We're only going to require one derivative in the end of U. Each component has to have the same derivatives, and we're going to build the boundary conditions into the space so that we're going to demand that each component of U is an H01 function. P, on the other hand, doesn't have to have any derivatives, so we can take P to be in L2. In fact, we're going to take P to be in this space, L2 0, and this 0 means that it's the subspace of the L2 functions that has the property that the integral of V over the domain is equal to 0. We call these mean zero functions. Mean zero functions. Okay, so this is the L2 space of mean zero functions. It turns out that's a perfectly good Hilbert space. It's a proper subspace of L2, and so we give it a special notation. Some authors will use, instead of writing it like this, which is what we're choosing to do, they'll use this notation. Okay, the over circ symbol. So this one is a bit more standard, I would say, so we're going to use that one rather than the latter. Now, why do I take P to be in this space? Well, if you look at this equation up above, then it's pretty evident that if I add any scalar, well, let's see, any constant value to P, then I'm going to get a solution to the same equation. If I start off with a solution to this equation, UP, and then I look at the function P plus alpha, where alpha is any scalar, that will also be a solution to the problem. So P is determined up to an additive constant for this equation. If you want to find a unique solution, then one way to do it is to eliminate that additive constant by demanding that your solution be in this space of mean zero functions. In that way, you can't add any constants to that function and get another solution. The only constant you could add to it would be 0. And the reason is because that's the only constant function which is of mean 0. So the choice of this space is so that we can get a proof of uniqueness in the end. In any case, what we do is multiply by that test function v, integrate by parts. We throw one of those derivatives from the Laplacian onto the v, and this p originally had a gradient. We're going to throw that over to the v, and when it goes over to the v function, it becomes a divergence, of course. And of course, this just means my usual L2 integration of f dotted with v. Okay, I'm going to do what I've been doing lately, and I'm going to drop the L2 subscript there. Anything that is lacking a subscript, you just interpret that as an L2 inner product. It's understood. I can also multiply the second equation by a test function. I'm going to use the test function q here. And the question is, do I want to integrate this equation by parts or not? The answer is no, because I want the test functions for q to be the same space as the function of the solution space for p. I've already determined that I want that to be just L2, so I don't want to add any derivatives to my test function q. I'm going to keep it as is. Now I can change this in a very simple way. The second equation, I can modify this by simply adding a minus sign. And you'll see we're going to do that later on. But it doesn't matter because it's entirely equivalent. I have a 0 on this other side. So it doesn't matter if I multiply by +1, -1, I can multiply by any number as long as it's not zero, and I won't change that equation. So this is my weak formulation, the weak solution for this problem. I multiplied by the test function, integrated by parts, and I get now two equations. Okay, so there's my equivalent to this first equation, and the divergence-free condition transforms into this condition here. Okay, so I'm looking for a pair of solutions, a pair of functions, u and p, with these regularities which satisfy this equation. Okay, and now it doesn't satisfy this equation pointwise anymore. It satisfies the equation in the sense of integrations, and so that's another nice part about the weak solution is it doesn't have to be or doesn't have to satisfy the equations pointwise. As we said before, f is a given function, and as usual, we can just assume that it's an L2 function. That's the simplest thing. Well, in fact, each of its components should be an L2 function. Now, when you do this integration by parts to get this term, this is the term that you're going to get. So we might as well define that. So what do we mean by this term? Nabla U, nabla V in the L2. Well, this is a bit weird because I need to be very precise about what this notation means. U is a vector, V is a vector. So when I take the gradient of that, I don't get a vector back. In fact, what I get is kind of a matrix or a two tensor. So, well, you can see the reason why that is the case. Well, actually, yeah, I'm gonna save that calculation for another time. Maybe we'll do it at the first part of the next lecture. So suffice it to say that this object here is now kind of like a matrix, as is this guy. So how could I put a matrix together with another matrix? Well, we're going to use what's called the matrix inner product of those two. Okay, so basically we have a matrix and a matrix in L2. These are matrix functions. So we're going to rewrite this as this integral, where we use what's called the matrix inner product. So hopefully you've seen this before. If I have two matrices, then this matrix inner product means that I take each component and I multiply by the corresponding component to B, and then I sum up all the components. That's exactly what I've done here. Now I can either, because of linearity, I can do this sum inside or outside this L2 inner product. But this is exactly what this inner, or how I'm defining this inner product. Okay, keeping in mind that when I take the gradients of these vectors, I get matrices. Okay, and maybe we'll address that next time with a little calculation, and I can show you how that comes about. But I'll assume otherwise that you are following along. Now, I'm also going to want to define the L2 norm of the gradient. And the easiest way to do, let's see, I don't need that square, that's a typo. Let's get rid of the square. So we're going to define this guy in exactly the same way that we always do. We're going to use this inner product, and we're just going to take and set the same, well, we're going to set V equal to U. Okay, so we just want the same function to appear in the first position and the second position. Okay, so if we take, right, so that's the usual definition. If I want to take, oh, I actually have it written down below. What am I thinking here? Right, so if I want the norm, I'm going to use the same function in both locations, and I'm going to take the square root. But now I've defined this object from here, and so that's the square root of the sum, I equals 1 to d. Now d is just going to be 2 or 3. That's the usual setting. I'm not going to be exotic and think about the Stokes equation in 10 dimensions, although I suppose you could. we're going to be setting d equals to 2 and 3. And for the later work we're going to do, we're going to concentrate on d equals 2. But in any case, this norm writes like this. Now, this actually is just a semi-norm for u, but it turns out that it actually is a norm if I restrict u to the space that I used above, namely this space. That's because I'm setting u to be 0 on the boundary. That's this the so-called no-slip conditions. And using Poincare inequality, I can show that this becomes a norm. So I'm going to actually show you how that works. So you should be able, with a little bit of work, and I'm going to leave this as an exercise to show that if UP is a classical solution and I multiply by a test function and integrate and do integration by parts, then that UP is also a weak solution. Going the other way is not so easy. You have to assume extra regularities, but certainly if I have a classical solution, then I can show that that's a weak solution. But the nice thing about the weak solution is, as usual, it doesn't require as many derivatives. Remember the classical solution, I required u, the velocity function, to be c2. For the weak solution, I merely require the velocity function to be an h1 function. A lot of what I'm going to be talking about in this section, where we're looking at the Stokes equation, is going to follow a book by my friend Bill Layton from the University of Pittsburgh. So his book is called An Introduction to the Numerical Analysis of Incompressible Viscous Flows, and it's from 2008. You can pick it up from SciAm. Quite a nice book if you're interested in understanding the numerical analysis of Stokes equation in particular. Now, we want to analyze, as usual, we want to analyze solutions to this weak formulation of the Stokes problem. To do that, we're going to be, it's useful to define a couple of really nice spaces. The first space is called the space of weakly divergence-free functions, or the subspace of such functions. So in this definition, we're going to define this subspace as a subspace of H01D. So this means that these are functions that are these are vector functions, each of whose components are in the space H01. That takes care of the divergence-free boundary conditions. It builds those divergence-free conditions into the space. And this bit here is what we call weakly divergence-free. Now, each V is in H1, so I can take its divergence. I hope you remember what the divergence operator looks like. Divergence means you take the derivative of each component of V, right? So what is the divergence of V? It's the sum, J equals 1 to D. Just take the derivative of the ith component with respect to the ith variable. Okay, you add them up. So weak derivatives are in L2. They exist and they're nice functions for such functions in this space. So I can calculate this guy. In fact, this guy you can show for such functions is in the space L2. Right? So that's a useful fact. If I know that V is a vector function, each of whose components are in this space, then its divergence exists, and it's an L2 function. And what about this Q? Q is going to be a generic function in L02. So this is my mean zero subspace of L2. And I'm going to demand for all such functions in this subspace that when I take the divergence of V and take its inner product with an arbitrary vector or an arbitrary function, sorry, Q, from this space, I always get 0. So this is like an orthogonality condition, right? It's kind of like an orthogonality condition, right? So if we give this space V a special name, special branding, it's called V. All right. Now, this object B that we're going to define as let's see. Yeah, got that right. Okay. So B is a bilinear form defined by this term. Where have you seen this term before? Well, this term Q dot gradient of a vector, or sorry, Q dot divergence. I'm saying that wrong. It's the L2 inner product of Q against the divergence of V, where V is some vector. That's a typo, missing the arrow. Where does this object come from? Well, you can see in our weak form, it appeared twice. So that object appeared here and appeared here. And so I could replace these two objects here by writing it as what's called the B bilinear form. And by the way, this object here is what we usually call the A bilinear form. And it doesn't have exactly the same structure as when we were talking about the Poisson problem, but it's very similar, and as I'll show you. So this object, bilinear form, its first input has to be vector function from this space, and the second one is a scalar function from these mean 0 L2 functions, and it combines them together to produce a real number. Well, that object is defined this way. And of course, this object I just pointed out to you, it appears in the weak formulation of the Stokes problem twice. What we want to prove is that this bilinear form is continuous. Okay, and I'll show you what we mean by continuous. As a consequence of the fact that it's continuous, V is a closed subspace of this vector space, or of this Hilbert space, actually. I didn't say that before, but this object here is a Hilbert space. And any closed subspace of a Hilbert space is itself a Hilbert space. All right, so how do we prove this? So the first step is to prove the continuity of B. How do we do that? We're going to use Cauchy-Schwarz. So let's look at this B. And by the way, what is the definition of the continuity for a bilinear form? It means that I can write B, or can estimate it from above by something which looks like this, okay? Where this has to be the norm on L2, and this is going to be the norm on that vector space that I talked about earlier, the H01D. Okay, so this is precisely what we mean by continuity. So once we get to the end of that, you'll see we've proven it. So we start with this object. There's that object by definition. Apply Cauchy-Schwarz. So Cauchy-Schwarz applies as usual. L2 norm of Q, L2 norm of the divergence of V. And I keep dropping my arrow on V. Now we're going to apply the triangle inequality to this object here. The reason is because this is the sum of three derivatives, right? That's the sum of three derivatives, or d derivatives, I should say, to be more precise. And so I'm going to apply the triangle inequality to each one of those. If I do that, then I get this object here. Okay, so going from here, I get here, applying the triangle inequality. Does everyone see that? It's a very simple application. Let me do it with two functions. If I had dv1 dx1 plus dv2 dx2, I should say two components, then this is less than dv1 dx1 plus dv2 dx2, right? Very simple triangle inequality. Now, if there are d components, then I've got d terms, and that applies in exactly the same way. So what you end up with here is a sum from I equals 1 to d of these terms. Now, remember I said whenever I have a vector function, then how many derivatives do I have? How many derivatives do I have? Well, you might remember a vector function has something called a Jacobian. So if I have a vector function, right, so that's got vector components v1, v2 and v3, say, what happens when I take the gradient of this guy? Well, so now I've got a bunch of components to my derivative, and I'm going to represent that this way: dvi dxj. I and j equals 1 to 3, right? I get a matrix of derivatives. Okay, so that's what we said above. Whenever I have a vector function, I take the gradient, I get a matrix of derivatives, or a two-tensor is what it's also called. So what you realize is that, well, this here is just like the diagonal parts, just the diagonal terms of this matrix. If I replace, if I want to come up with something bigger and a larger estimate, then instead of just focusing on the diagonal terms of that, I could use all the terms in that matrix. So in other words, if I want to replace this by something larger, we could replace it by the sum I equals 1 to d, sum j equals 1 to d of these objects here. Okay, so great. But this object is not quite the derivative that I defined above. The derivative I defined above looks like that. What do we have? We have something that looks like this, right? So if I really had the right object, it would be something like that, which is not what I have. So I'm going to play a trick. I'm going to use Cauchy-Schwarz, and it's going to be, well, what type of Cauchy-Schwarz should I use? I'm going to use the discrete Cauchy-Schwarz. What do I mean by discrete Cauchy-Schwarz? So discrete Cauchy-Schwarz said if I have sum I equals 1 to 3, let's say, vi wi, then that's less than v's norm and w's norm. But what norm am I talking about? I'm talking about the discrete 2 norm, okay? The discrete 2 norm. That's Cauchy-Schwarz. Okay, it's kind of the basic Cauchy-Schwarz, maybe the first one you've seen. I'm going to think about this summand as being this times 1. Okay, and instead of having a Cauchy-Schwarz where I'm applying it with a single summation, I'm going to apply it with a double summation. I can still do that, no problem. So when I apply Cauchy-Schwarz here, again, I'm treating the summand as being this term times 1. Then what I get on just replacing this object using Cauchy-Schwarz, I get the sum of that term with a square root, sum of that term with a square root. Well, this term here is just going to be, if I look at it, it's just d squared, and I'm taking a square root, so I get d. What about this object here? Now that I've used that discrete Cauchy-Schwarz, I've converted that precisely to the norm object that I defined above. So that means, and of course, that's the usual norm that I'm using for that space. We'll show momentarily that it actually is a norm using Poincare inequality. But hopefully you believe that even before seeing it. So what do I need to get continuity? I just need some constant here. And well, the constant is actually d. All right, now I want to show that this space is a closed space. So what I need to do there is let's take a sequence of functions from this space, okay? Or yeah, sequence of function from that space, and we're going to suppose that it converges to something else. Well, if it converges, it's not necessarily going to converge to something in this space unless that space is closed. So let's take a sequence that's entirely in this space, V, and we're going to assume that Vn converges to V in this bigger space, okay, H01. I want to show that actually that means that this V has to not be in this bigger space, but actually in this smaller space. If you think about it, it's like this. The picture is here. There's my big space, H01D. And V is some subspace in there. And I've taken a sequence of functions that converges to a point. And what I'm going to try to show is the point to which it converges ends up back in V. Well, if I just know that it converges, then I don't necessarily know that it's back in V. If it converges is something it's going to be in the bigger space. Let's try to show that it's actually in V. Well, we have continuity. Okay, we have continuity. And so let's take how would we know that this function is in the space V? Well, it would be in space V if this guy is identically 0. That's how we define that space. So if that object is 0, if this object is 0, then I know that V has to be in the space. This function V has to be in the space capital V. Now, what I'm going to do is I'm going to use the linearity of that bilinear form B. It's clearly bilinear. It's linear in both components. So I'm going to add and subtract Vn. Add and subtract Vn. Well, Vn, by my assumption, lives in V. And what it means to be in V is that B of Vn Q is equal to 0. What about this guy? That's what's left. Well, I can use the continuity that I just arrived at from above. Missing something. My missing thing is D. Forgot that constant. So Q just goes to here, and whatever is here goes to here. But I know that this guy converges, right? In H1. So that means that this norm goes to 0. That guy goes to 0. Well, what is that saying? That says that this guy, which doesn't depend on n, the only possibility is that that is exactly 0. The only possibility is that that is exactly 0. But that just means that V is in capital V. Maybe let's write that as 2 steps. Okay, so the first one is the only possibility is that. This implies that V has to be in capital V. And that, because this guy was arbitrary, that implies that V is closed. Period. Okay? Now, the only other step is that just to realize that any closed proper subspace of a Hilbert space is itself a Hilbert space. If you've taken any course in linear analysis, we have this course in applied linear analysis here at UT, or functional analysis. This is a very simple thing that is proved very early on in such a course. We haven't proved it here, but if you don't know the proof or you haven't seen it, just take my word for it that every closed proper subspace of a Hilbert space is itself a Hilbert space. Or better yet, try to prove it for yourself. Now, I've alluded to the fact that this object here is a norm, and the way we can prove that it's a norm for this space is to show some sort of Poincare inequality. So that's what we're going to do next with this next theorem. There is a constant, C greater than 0, such that V L2, or sorry, U's L2 norm is less than a constant times the L2 norm of the gradient of U. And once again, I've forgotten my arrow symbol. This is true for all U in this space. And the important part here is that the boundary condition, that no slip boundary condition is built into the definition of the space. How would we define this norm, this L2 norm? So the way that that's done Just a second here. Lost my cursor. Can you guys still see the screen? Give me a thumbs up if you can.
Yeah, we can still see.
Okay. Yeah, something happened to my screen, but as long as it's still working, we'll go with it. Okay, so how do I define this norm or this inner product? Well, this inner product, these are no longer scalar functions. So what I'm going to do is I'm going to sum up the components. I'm going to take the dot product of the components of u and v, and then I'm going to integrate in L2. So that's how that's how that inner product is defined. And of course, the norm is just defined by taking the square root of this guy whenever I put u in the same location, first and the last position. Okay. I think that's all there is to that. Okay, so let's prove this. Suppose that u is an h01 function, and what I mean in particular is that each component of u has to be from this nice space, right? So that's what I've just said there. ui is an h01 for I equals 1 to d. So we're going to break this up into a couple of steps. So let's square that L2 norm. Missing L2 there. Square that L2 norm. There it is by definition. And each component is in H01, so we can apply the Poincare inequality component by component. So there's a Poincare constant, we're just going to call it generically C. Each one of these guys is less than the gradient of UI, right? Gradient UI. That's just the standard semi-norm that we've defined previously. This is the one you've seen many, many times. And let's see, what am I doing with this guy here? Okay, so this guy we're going to unpack. So let's write this using what it is. So this is the gradient of, right? That's the L2 norm of the gradient of UI. And that is exactly equal to this object right here. Okay, because we're squaring it, we just get this guy. But now you notice that I have a sum I equals 1 to d out here. I've got this inner sum, j equals 1 to d. And because I'm squaring it, this is exactly, by definition above, this L2 norm of the gradient of u squared. Now that in and of itself doesn't show that this is a norm for this space, but if you realize what a normal norm would be, so the norm would be comprised of two objects. The L2 part and precisely this part. But now the Poincare inequality says that this is less than an object which looks like this. So that says that this is less than 1 plus that C, running out of room. Okay, so that shows that I can bound this object from above by a constant times this object. And of course I can bound it below. If this really is the composition of that norm, then I can simply throw this term away and bound it below by, again, didn't give myself enough room. Okay, so this shows that this object and this object are equivalent. So this gives us a bona fide norm on that space. if you believe that this is how you would define the norm ordinarily, and it isn't so hard to show that that's the case. All right, so maybe we, because of the importance of this, probably should have made that into a separate theorem, but as long as we have it to refer to, that's good enough. All right, so like we've done many times with the other equations we've looked at, like the Poisson equation, we've rewritten them in fairly generic terms. And so we're going to do the same thing with the Stokes equation. So to do that, what we've got one of the parts down. We've got this B uh, thing that this B bilinear form that we've already defined. Let's go ahead and define this object called the A bilinear form. Well, the A bilinear form is going to look exactly like that one that we derived or defined for the Poisson problem. It's the gradient of U, gradient V, L2 inner product. The only difference here is that, importantly, the functions U and V are no longer scalar functions. They're vector functions. They're fluid velocity fields. And so this guy has a little bit of a different look and feel because of that. It has, in this case, two sums rather than just a single sum. The second bilinear form that I want to define is that one that I've already addressed. That's guy that appears twice in the weak formulation of the Stokes problem. This object called the B bilinear form. Okay, defined exactly the same as before. Then these two definitions allow us to rewrite our weak formulation of the Stokes problem in this way. Okay, so there's the A form. That's grad U, grad V. B, this guy. Okay, so notice that I'm putting, let's see, did I define that? Let's see. I've got a typo here. Let's see, I've gotten my variables mixed up. Here I've put a velocity first and a scalar field second, and I've messed it up there. So I think let's go back and make sure that we're consistent. How did we define it before? Yes, velocity first, scalar. I guess you could call it velocity and pressure. Velocity first, pressure second. So down here, so this is still correct, but this guy is not. So this is our typo. And that is also in error. So what should it be? It should be P. No, it's going to be V, right? And P. And down here, it's going to be U and Q. I think that's correct now. Now, the only difference is that I put a minus sign here, and there was no minus sign previously, but the minus sign can simply be added because I'm setting everything equal to 0 anyway, so it doesn't change anything to put that minus sign. So previously it was written with a plus sign, change it to a minus. So this, it turns out, has the form of something called a saddle point problem. Okay, saddle point problem. Now, I don't have a lot of time to go into why it's a saddle point problem or has that structure in this course. So I guess you can look that up on your own, do a quick chat GPT search. You know, what does a saddle point problem look like? Well, in weak formulation, this is precisely what a saddle point looks like. In fact, we can write it in fairly general terms. If A is a bilinear form on this space X, and B takes functions, it's a bilinear form on X cross Q, and F is some linear functional and G is some linear functional, f is a linear functional on the space x and g is a linear functional on the space q, then the generic form of the saddle point problem, let's slide this back a little bit, is as follows. So the only difference with the problem that we have is that we don't have a term over here. In our case, this is just equal to 0. Otherwise, you can see that this really looks a lot like the weak form of the Stokes problem. So that's why sometimes the Stokes problem is called a classical saddle point problem. It has that form. So you can just put that in your pocket. It's not going to be extremely, um, it's not going to be necessary for our discussion at all, but it's an interesting fact. Okay, so now, so I want to make a realization. We want to show that U has a weak solution, and then later we want to show that actually U and P, or I said no. Let me restate that. I misspoke. We want to show that there's a unique weak solution to this problem, to the Stokes problem, but it's not easy to do it. There is a version of the problem which is easier to show existence and uniqueness for. And that's what we're going to tackle first. We're going to get the low-hanging fruit first, and then we'll tackle the harder question momentarily. So the first thing I want you to realize is if U and P is a weak solution to the Stokes problem, that is, it solves that 22.2. Let's scroll back up really quickly. Satisfies this equation. Okay, these two equations, in fact. If U and P are a weak solution to the Stokes problem, then it has to solve this. But notice that if this happens, then the second part of the solution says that this function U has to be in the space V, because this defines what it means to be in the space V. U has to be in the space V. All right? So, therefore, if I know that I have a solution to 22.2, then automatically U has to be in the space V. Okay? U has to be in the space V. So that means if I restrict my test functions not to H01, but to the space V, then the equation that I have to solve is just this guy. Well, the second equation is precisely this statement here, okay, for U. This one's for the generic V, but U being in that space V means that it satisfies that guy. So the second equation is taken care of. I don't have to even write it down. By simply mentioning that my solution is in the space V, that takes care of that second equation. Now, V is a subspace of H01. We just said that, right? We said that V is a subspace of H01 and is a proper subspace. So normally the test functions are in H01. But if we restrict the test functions in H01 to be simply in the space V, then what happens? Well, that second term that was here in 22.2 goes away. That guy vanishes. And all I'm left with are these two terms. So I'm claiming if U is a solution to U and P, but actually both, is a solution to 22.2, then clearly U is in V. That's the second equation. And if I restrict my test functions to be not from H01, but from the subspace V, then this equation must hold. So this says that if U and P solve 22.2, then U alone solves 22.4. So I hope everybody sees that little bit of logic. If U and P solve 22.2, then U alone solves 22.4. I've had to make a restriction for my test function space, but there's no problem doing that. Now, suppose that F is restricted a little bit further. Suppose that it's a linear functional on this Hilbert space V. Okay, so that means it's in this set we called V prime. That's the space of linear bounded linear functionals on V. Then this problem has a unique solution. And the reason it has a unique solution is because of the Riesz representation theorem, or alternatively, due to the Lax-Milgram theorem. And I'll show you that in a minute. The other part of the Riesz representation theorem says that the solution U that I derive when I use the energy norm, so this is the energy norm, okay? And by the way, this is what I'm going to use as my notation for the H1 semi-norm for vector functions. That's just the derivative part of the norm. This guy, the H1 semi-norm of U is equal to exactly the operator norm of V and V prime. And the operator norm of V and V prime, sorry, the operator norm of F in V prime is precisely given by this. This is the definition of the so-called operator norm. So all of this stuff will be free. This part here comes directly from Riesz representation. The uniqueness of the solution comes from Riesz representation here. As long as I can show that this is a coercive, continuous, symmetric bilinear form. It's clearly symmetric, it's clearly coercive, or it's clearly continuous, and it's clearly bilinear. The only question is it coercive? So this object here is a coercive bilinear form, and that's due to the Poincare inequality. The proof is exactly the same as the um, for the Poisson equation. It's really more or less exactly the same. What am I saying then? What I'm saying is if you redefine your problem so that you're looking for specifically for the problem solution in the space V, then you know beyond a shadow of a doubt that you have a solution, and that guarantee is given to you by the Riesz representation theorem. Full stop, and nothing more to say. So this problem has a unique solution given to us by Riesz representation theorem, but we have to restrict our attention to this Hilbert space, not the original Hilbert space that was given, but to this space V of weakly divergence-free functions. Okay. Now the reformulation of the problem, which is for which it's easy to get existence and uniqueness, gets rid of the pressure. So we don't know anything about the pressure, and that's a problem. This space, it turns out, is not easy to work with. Okay, this space V seems nice, but it's not easy to work in that space V, especially when we're trying to build finite element schemes. And that's because getting a conforming finite dimensional subspace, finite element space, for that space V is very hard. So we don't want to work in that space for that reason and reasons that are kind of beyond the scope of our discussion. So we need to figure out. We now know that U exists. U has to be in V. But what about that pressure P? We need to know something about that. To know something about that, we're going to have to do a little bit more work. We have to create something called the nth sup condition. Okay, the nth sup condition, which turns out to be very powerful and very useful for the finite element methods. We won't be able to have a complete and full discussion here about this, but if you ever take the 600 level numerical PDE course, 673 and 4, I believe it is, then you'll get into that discussion there, and Dr. Salgado usually goes through that in a lot of detail. All right, to understand the nth sup condition, we need to define a little bit more machinery. So we have that space V. We're now going to define a space called V perp. So this is what is usually called the orthogonal complement of V with respect to the bilinear form A. By the way, we now know that A is actually an inner product. Here's the definition of the orthogonal complement. And by the way, it always goes this way. So it's the set of all functions v in H01D. Again, vector functions, each of whose components is in H01, such that AVU is equal to 0. So this is the orthogonal bit, right? Anytime I have an inner product and I find that when I test some function against another family of functions, I get 0, then I say that V is orthogonal to those things U. But in this case, U is a set of all objects in that weakly divergence free space we called V. Okay, so this is called an orthogonal complement. And to define an orthogonal complement, you just simply need a couple of things. You need a subspace. There's our subspace. I need an inner product. There's our inner product. And that defines an orthogonal complement to this subspace. Given any q in L02, this is the L2 functions that are mean 0, there exists a unique v in V perp such that divergence of V is equal to Q. Okay. So the proof of this statement here, and of course the rest of it, is non-trivial. So we're not going to prove it in this class. We're going to simply defer to this this reference, Geralt and Ravier, a very famous book on numerical methods for Navier-Stokes equations. But we're going to use it in the construction of that nth soup condition that I keep alluding to. So given Q, given any Q in L02, so mean 0 space of L2 functions, there exists a unique V in V perp, that perp space that I just defined, such that the divergence of V is equal to Q. So we don't know if we can prove this, probably too difficult for us to prove using the machinery that we know, but let's make sure that it makes sense. Well, divergence of a vector function, that's a scalar function. And this object is also in L2, right? Q is a scalar function in L2. Is it possible that they are equal to each other? Yeah, it's possible, right? Now, scalar equals scalar. Is this object over here, can I show that this object is actually mean 0? Well, you can integrate this over the domain, and you can show pretty easily using the divergence theorem that this guy has to be mean 0. So everything makes sense. Mean 0 L2 function equals mean 0 L2 function. It's just that proving that it exists is a harder thing to do. Once we know that it exists, we also have an estimate which looks like this. Okay, there is some constant C which is independent of Q, such that that solution V in the H1 semi-norm is less than a constant times the L2 norm of Q. Okay, so that's a fairly important result. We don't have time to prove that, so we'll just use the reference Geralt and Ravier from 1986, fairly famous book. If you get deep into finite element methods at any point in your life, then you'll be interested in that reference. Well, finite element methods and finite element methods in particular for Navier-Stokes. That's a good reference to have. All right, I'm going to have time to state the inf soup condition, or I will actually call it a precursor to inf soup condition. We won't have time to prove it, and so I'll simply state it, and then we'll use it next time. We'll restart our analysis from this point. So there exists a constant beta greater than 0, such that the inf soup condition is quite difficult to figure out and understand, but we want to show that the supremum of objects over here. So this object, this quotient depends on V. When we take the supremum of that, then that gives us something which is completely independent of V. Okay, so this quotient, once we take the supremum, is independent of V, and that has to be bounded below by a constant, which is independent of Q times the L2 norm of Q. Okay, this has to hold for all functions Q in this space of mean 0 L2 functions. So the proof of this uses this last result, which we didn't prove. That last result, the proof of that, well, that fact, this result, will help us to prove this result. And it's a little bit curious, the structure of this, but all of these terms, the best way to say it is, um, you it's very difficult to figure out why it should be this quotient in particular. Why is that useful? Well, it just so happens that when we're doing a certain construction, this guy pops up. Okay, it pops up again and again, and so this object, this inf soup condition becomes important. But we've run out of time to discuss why that's so, and so we'll pick up with our discussion there next time, and we'll prove this using that last estimate or that last fact, and then I'll show you why that this is useful in showing some properties of the Stokes problem. That'll have to wait until next time. Okay, that's where I'll end, and I'll take your questions now.